climate of the past is not the guideline for the climate of the future. It will be different. How much different depends on what we do on our greenhouse gas emissions. But the reality is it is different now than it was a decade ago. It will be different again in another decade.
What's causing climate change is pretty basic science. It's physics and chemistry you learn probably in grade 10. The lag effect is pretty large, so even if we stop today, it's going to take a while for things to sort of go back down to normal, if they even go back down to normal. You know, they might just become a new equilibrium.
We have a very uneven distribution of water around the world. And of course, with climate change, we have changing stores of water, changing availability of water. It's predicted that a lot of the future conflicts between nations, wars, are going to be fought over water.
The science is in. It's time for action. And we've been very frustrated by how slow the action has been. We're not saying everything's been understood, but we know enough. We know enough that, for example, smoking cigarettes is linked to cancer. We know enough that what we're doing is changing the climate, and it has very dire consequences.
Typically we take out insurance, in situations where it is unclear to us precisely what the consequences will be. We know that they are expected to be severe. We don't know precisely how severe. We know that the impacts will be negative. Negative in terms of increasingly severe and frequent extreme events in precipitation and drought, which are already being experienced all over the planet. We continue to fail as a human civilization.
Earth has become a lot more efficient over the last decades. Yet, when we look at the carbon production, that actually hasn't been reduced. So what happened? People actually drove more cars, and they drove the cars more often. So it is really a behavioral aspect, and so we need to understand how can we actually change people's behaviors.
I think humans aren't stupid. I think we may be doing things more slowly than we could be or should be, but I think as the evidence mounts, eventually we're going to see that we need to do something.
Instead of wasting time in discussing the existence or convincing those who are not convinced that the climate change is occurring, we are trying to move into the area of decision making under uncertainty.
We live sort of in the present, and we keep thinking the present is the way it always has been. But when it comes to environmental issues, one of the key issues is, are things changing? And if so, why? And what's the cause of the change? For this, we need long-term data. It's very similar to human health. If you go to a doctor, one of the first things a doctor asks you is your medical history. They want to know what your baseline is. Are you really sick is what they're in some ways trying to get at. The same thing's with the environment.
We do have long-term data records for certain gases, and we can very clearly see human activities having an impact. Kind of the two classic long-term data sets are the Mauna Loa record of carbon dioxide and the Halley Bay Antarctica record of stratospheric ozone. And those two records, they both began in International Geophysical Year back in 1957, and really those are kind of two classic data sets that really have shown us how the atmosphere has been changing over time.
Since the advent of radiocarbon dating, it's been possible to reconstruct measurements, time series of the history of relative sea level change, that is, the change of the height of sea level with respect to the land, by basically interpreting indicators of relative beach elevations and measuring their age using the radiocarbon dating methodology.
The Arctic is really a bellwether for climate change. As people may know, climate change in the Arctic is happening more quickly than elsewhere in the world. Temperatures are rising more quickly than they are elsewhere in the world, and so there's a lot of interest in trying to understand what's happening in the Arctic and why, and how it's going to evolve in the future.
What are some of the main parameters that impact today's changing sea level?
Well, there are really two main sources of present-day sea level rise. The first of these, and in many ways the most dramatic, is the impact on sea level rise that's associated with the melting of large accumulations of land ice on the continents. In particular, the Greenland ice sheet and the Antarctic ice sheet, which are very, very well known to be melting at an increasingly rapid rate. A second contribution is that which comes from what we call the steric impact of the global warming process. As the water in the ocean warms up, the volume of water in the ocean expands, and this leads to a rise in sea level. But there's also a missing component, which we still do not adequately understand, which is also associated with the loss of land ice from what we call small ice sheets and glaciers. The total rate of sea level rise, which we're observing with the altimetric satellites, is around 3 millimeters per year. Global sea level is rising as a consequence of the melting of ice from Antarctica at the rate of about 0.3 of a millimeter per year, as compared to the 0.6 of a millimeter per year, which is coming from Greenland. And remember, if we add these two contributions together, we get something less than 1 millimeter per year. The steric effect is contributing something like 0.5 or 0.6 millimeters per year most recently. And so we're missing about 1.5 millimeters per year, which we're obliged to ascribe to the melting of this very large collection of small ice sheets and glaciers. Modern tide gauge measured rates of relative sea level rise, the impact on GRACE measurements, the impact on altimetric satellite measurements, all of these data are very significantly contaminated by the influence of what we call glacial isostatic adjustment, associated with the loss of the huge accumulations of land ice that existed primarily in the northern hemisphere at the last maximum of ice age occurrence, which was around 20 to 25,000 years ago. It turns out that the shape of the Earth is continuing to change as a consequence of the meltdown of the last of these massive glaciation events, which led to a rise of sea level of, on average, about 120 meters. The main change in shape is the change in shape from a shape which is more curling rock-like, more squashed at the poles, right, to a more spherical shape. And that squashed shape at the poles was actually produced by the large ice loads that existed on the poles at last glacial maximum. So when these ice sheets were eliminated, the fluidity, if you like, viscoelasticity in physical terms, of the planet allows it to rebound slowly back towards a more spherical shape after the ice load on the poles has been removed. Because of these particular changes in the Earth's shape, we're able to actually monitor the ongoing changes in shape by using observations of the Earth's rotational state itself. And again, the theoretical models that have been developed to allow us to predict local changes in the Earth's shape through relative sea level histories, that same theory enables us to make predictions of what the changes in the Earth's rotational rate should be, and those changes, those observed changes and that fit of those changes to the theory allows us to confirm what the internal viscosity of the planet must be, and further confirm the close connection of the analyses of sea level history, planetary shape, sea level rise, to internal, much longer timescale, internal dynamical processes associated with plate tectonics. And it has been argued that 3 million years ago, sea levels were dramatically higher than they are at present. This is the so-called Pliocene warm period. The carbon dioxide load in the atmosphere was about equal to modern, that is around 400 parts per million by volume. It's been argued that sea level at that time was higher by 22 plus or minus 5 meters than it is at present. Right? Now it's known that at that time the Greenland ice sheet did not yet exist 3 million years ago. It formed after about 3 million years ago. But the Greenland ice sheet only involves, in terms of eustatic sea level rise equivalent, about 7 meters. If we were to add to the budget the loss of all of the ice from West Antarctica, right, at that time, that would give us perhaps another 5.5 or 6 meters. Right? So there would still be a missing 9 meters. Right? that would have had to come from East Antarctica. So think carefully about what this might mean. It would mean that on a very long time scale, right, if we were to sit locked in the present day carbon dioxide concentration regime, and we were to wait long enough, right, for the long time scale feedbacks to fully come into play, which involve the loss of land ice, right, then we would lose all of Greenland, we would lose all of West Antarctica, we would lose a big chunk of at least coastal East Antarctic ice. Again, mantle convection effects, plate tectonic effects, may have contributed to these estimates of the amount by which sea level was higher during the warm Pliocene. One of the regions which has been most studied, especially by the American scientific community, is the region of Pine Island Glacier, in West Antarctica, which is in this region of the Amundsen Sea sector of Mary Birdland, which Grace observes to be losing mass at the highest rate of anywhere over the Antarctic continent. But in that case, the influence on the destruction, if you like, of the Pine Island Glacier is not coming from warming above. Okay? It's actually coming from the impact of warm ocean water attacking the ice shelf that's connected to the glacier, right? And by destroying the ice shelf, eliminates the buttressing effect that it has on the rate at which the glacier can flow towards the sea. And so by eliminating this buttressing effect, the warming of the ice shelf from below by anomalously warm ocean water has led or is leading to continuing wastage of ice through Pine Island Bay. So this process whereby, or the processes whereby land ice is lost to the sea, thus leading to a rise in sea level, are really rather complicated. Greenland can lose ice relative to gain by anomalously fast melting at the surface, what we call surface mass balance. But also because of melting during the melt season on the surface of the Greenland ice sheet, we can make meltwater percolate down to the base of the ice sheet through what we call moulins, great crevasses, if you like, in the ice. And once this water makes it to the base of the ice, it may so lubricate the base of the ice sheet, right, that it's able to dynamically flow much more rapidly towards the sea than would normally be the case in the absence of that meltwater lubrication. So wherever you look and discover that land ice is being lost to the ocean, thus leading to a rise in sea level, there are a complexity, if you like, of processes which are contributing or may be contributing.
In spring of 2011, we had very severe stratospheric ozone depletion. We were right there in Eureka, and the chemistry that was destroying ozone was kind of more or less right overhead. But we could compare those with measurements that had been done at Eureka for the previous 15 years. And so we had a fairly nice baseline to show that the ozone depletion that year was at a record low level. And some of the chlorine compounds, nitrogen compounds that are involved in chemistry were also abnormally low. That the stratosphere was unusually stable and very cold that winter. And so the chemistry that leads to ozone depletion relies on very low temperatures. And that's why we tend to have an Antarctic ozone hole, but not an Arctic ozone hole, because temperatures in Antarctica get much colder because the conditions in the winter are just much more stable than they are in the northern hemisphere. Greenhouse gases are trapping more heat in the lower atmosphere, but in fact that's actually cooling the stratosphere. Okay. And so if temperatures in the stratosphere are colder, some of the chemical reactions that destroy ozone will tend to slow down. And so in fact we expect kind of globally that will help ozone recovery. On the other hand, if the stratosphere gets colder in the polar regions, so in the Arctic and the Antarctic, if it's colder in the stratosphere, then the conditions that lead to ozone depletion in the spring will be enhanced. And so we may see more ozone depletion in the polar regions in the springtime. So there's these kind of two competing effects. My research involves doing measurements of atmospheric composition. So we use a variety of different instruments and techniques to measure gases in the atmosphere. So those measurements are of things like greenhouse gases, so carbon dioxide, methane, nitrous oxide. We also do measurements of ozone and gases related to ozone chemistry. And we also measure pollutants in the atmosphere, things related to air quality. The end goal is to try to understand what gases do we have in the atmosphere, how are the concentrations changing with time, with location, and trying to understand the underlying kind of chemistry and physics that determines the amount of gas in the atmosphere. We do measurements at a lab on Ellesmere Island called PEARL, the Polar Environment Atmospheric Research Lab. And there we have a suite of about 24 different instruments that do measurements of the atmosphere from the ground to roughly 100 kilometers. And so we're measuring a wide variety of different atmospheric variables there, temperatures, winds, aerosols, clouds, and trace gases.
So the gases that you measure, are they normally from a local source, or are they transported long distances? What's the difference?
Well, one of the advantages of living in the satellite age is that we really can see, how gases are emitted and then transported around the globe. And so, for example, back in 1999, NASA launched a satellite called Terra, and one of the instruments on that is an instrument called MOPIT, which was actually developed here in Canada by Professor Jim Drummond. And so MOPIT was really one of the first instruments to measure carbon monoxide, which is a pollutant. It comes from fossil fuels. It has a number of different sources. And carbon monoxide has a fairly long lifetime of several months. And so that means that when it's emitted in the atmosphere, it sticks around for a while. Okay? And that means that you can really see how it's being transported. And so there are these beautiful movies from MOPIT that kind of show you kind of in a time-lapse way how carbon monoxide being emitted from Los Angeles Basin gets transported across the states and eventually over to Europe. Big emissions in Western Europe get transported over Russia into Asia. Emissions from China, they get transported across the Pacific. And with these kinds of measurements that we can see from satellites, you can really see these transport pathways where pollutants emitted in one part of the globe very clearly get transported elsewhere.
It circles the globe, and so that it affects the global atmosphere. So the emissions of CO2 from Ontario, from some part of China, from some part of Russia, Africa, they're all mixed together. They all contribute based on how much we put up there. And the result is the climate is changing. The climate is already warming at about 0.2 degrees C per decade for the last 25 years. It's projected to continue that way because of this very long lifetime of the CO2 in the atmosphere.
We know how greenhouse gas molecules work. We know how they like to move. And we know how they interact with radiation. So it's pretty basic science. It says if you're putting more of those molecules in the atmosphere, they're going to absorb more radiation. Treating the atmosphere like a big black box, that black box is going to heat up.
So what are some of the effects due to climate change, and why would we as Canadians care about this? Especially why would we as youth care about this in somewhere so remote as the Arctic?
Yeah. Well, what happens in the Arctic really affects us all. No one who knows anything about climate has argued all of climate is human. But we can pinpoint that things have been going very oddly over the last 100 years. We can pinpoint this is human related. This is not part of natural variability. And we've seen some striking changes. We've shown, using our fossil methods, we've shown that the climate started changing about 100 years ago, and it's been accelerating. So we often refer to the Arctic as the sort of like the miners' canaries of the planet. It's the first to show signs of environmental change to the greatest degree. Every time you see a lake and pond, it contains a history of that environment, and that's because lakes slowly fill with mud. 24 hours a day, 365 days of the year, lakes slowly fills with sediment at the bottom of the lake. That becomes like a history book or a time machine. The deeper you go, the older it is. We have ways of removing that history book and also looking at the information contained in those layers. There's all sorts of information at the bottom of the lake. There's fossils of what lived in lakes. They're just tiny. They put hundreds on the head of a pin. But some of these species like cold water, some like warm water, some like lots of ice, some don't like much ice. Some like acid water, some like alkaline water, some like polluted water, some don't like polluted water. Since we know what these organisms require, and we can find their fossils going down in history, and we have independent ways that we can date how old it is. We can say this is the 1820s, this is the 1750s, this is 500 years ago. We can see how these organisms assemblages have changed over time. And by looking at that, we can reconstruct how the environment has changed. And we've been sampling a series of ponds and lakes near Cape Herschel. And we've been working on these about 40 ponds going back since 1983. Based on our fossil analysis, we could show that yes, indeed, the climate has been changing over the last century. And we couldn't link it to natural causes. It seemed to be linked to humans. And we made the predictions that if this warming continues, eventually these ponds, which we knew have been their permanent water bodies for thousands of years, would simply evaporate away. Well, that prediction came true over the last decade or so. We slowly watched these ponds change, and they got shallower and shallower. And we were also monitoring the water chemistry. And as time went by, they were getting a little saltier. And that's exactly what you'd expect. It's like putting a pot of soup on the stove and taking the lid off and leaving it at low heat. If you watch your pot of soup, two things happen. One, the soup level goes down as the water evaporates. We could see that happening in our ponds over the years. If you keep tasting your soup, it's getting saltier and saltier. That's because the water is evaporating away and the salts are being left behind. We were measuring the salt each year very carefully, and we could show the steady increase in salt. Well, starting in about 2006 or so, some of these ponds started evaporating completely. So these were ecosystems that have been there for thousands of years, and now they're gone. Even worse, perhaps, when you're on Cape Herschel, is the wetlands. Wetlands are very important, especially in Arctic regions. They take in greenhouse gases, and they're very important ecosystems. Well, there's some wetlands near Cape Herschel, and we were watching those wetlands too. And back in the 1980s, these wetlands were full of water, still full of water, nice, healthy ecosystems, green. Come back in the last few years, they've so dried up they've died. Many of the plants have died in the wetlands. You can actually put a match to it and they'll burn. People have done very similar type of work on lakes all across the circumpolar Arctic, and I think we had over 50 examples right across. It went from Norwegian Arctic to the Russian Arctic. We had examples all over. And we could show the same types of changes happening across the Arctic. It's not something localized, it's not a Canadian issue, it's a circum-Arctic issue. People are using the same methodologies now in the Antarctic and the sub-Antarctic in the southern hemisphere. And they're finding the same types of things. They're using our same sort of fossil analysis to show changes happening. They're seeing some ponds starting to increase in salt content. The same things are happening in the far south as well. So this is a global issue, it's not just a Canadian issue.
Forests are constantly exchanging two big greenhouse gases, water vapor and CO2. Water vapor we don't really worry about from a climate change point of view because it cycles so quickly between the atmosphere and the surface, but CO2 is a big one. When you're looking at a healthy, sustainable forest system, you want to be taking in more CO2, storing it either in its tissue or as material in the soil, then it's releasing back to the atmosphere. So you want them to be happy and productive enough that they're taking in more CO2 than they're releasing back to the atmosphere. So as a tree grows, it grows leaves, and in the senescent season, most of them drop some of those leaves. Even conifers will shed needles, and as it does, it starts to break down and forms organic soils. So there's your carbon in the soils. Forests store less than a wetland would, because wetlands are usually covered pretty extensively by different types of mosses, and the mosses can grow several meters thick, and they tend to decompose a lot slower. So the bigger they get, the more water they need. So there's a link there we want to keep in mind to water cycling. We have to pay attention to how permafrost is melting, how that's affecting water and energy movement through the landscape, and how that feeds back to the atmosphere and the climate. How long that ice sticks around really determines how much water the plants at the surface can use. So there's going to be a pretty strong linkage, we think, with productivity. And whenever you impact the productivity of a natural system, you're affecting how much CO2 it can pull and keep out of the atmosphere. And a lot of debate and research now is what is that transition zone, which is really from the boreal forest into the subarctic. A third of the world's carbon is stored in that zone. So as we start to change productivity, especially start to thaw some of that carbon, there could be really important feedbacks. That's carbon that's been accumulating for hundreds of years. But more importantly, probably in that region, is the carbon that's in the soil. That's where most of the carbon is stored. And a lot of that, especially as you go north, is protected because it's encased in that permafrost. so it can't decompose, it can't be released to the atmosphere. But when you start to thaw that in warm temperatures, microbes are all of a sudden going to wake up and you start to lose a lot of that carbon stored in the soils.
So what would you say some of the major challenges are facing a society with respect to water?
Right. Well, I'd say that we have significant challenges ahead of us with respect to water quantity and, of course, with respect to water quality. Groundwater is really, next to the ocean, the largest source of water. And, of course, we can't drink from the ocean without a lot of engineering and energy involved. So groundwater is really our largest reservoir of fresh water in the world, representing about 2% of all our water. By comparison, the lakes and rivers, from which we draw much of our drinking water, represents only 0.007% of all of our water. Of course, water is overall a renewable resource, but as we know, groundwater flows very slowly, is replenished very slowly, and in many parts of the world we're over-pumping the groundwater, which is causing groundwater tables to drop dramatically. It's causing subsidence of the soil. In many parts of the world, we're polluting the groundwater by dumping industrial chemicals, by a lot of our fertilizers and nutrients that we're applying to the land, pesticides, pharmaceuticals.
We're seeing noticeable changes in whole ecosystems. Anywhere you see a change, that the effects of that change are being propagated through the whole system. And I think that's one of the challenges the climate community faces now, is trying to better understand, these effects.
Climate models that are predicting more droughts in some regions, more floods in other regions, more hurricanes as we've got more heat in the oceans.
Sea level is rising. If you have more storms, you get more what's called a storm surge. The winds push the water up over the land, and as we can show by documented evidence, we are having more intense precipitation events already. Those changes in heavy precipitation events are directly related to the increasing amount of human-caused greenhouse gases in the atmosphere. It's not just random, they're actually going up. Now, water is a huge issue. We either have too much or too little. The situation of extended drought conditions costing economically, jobs, as well as environmentally, huge impacts in this decade. And we're getting more intense precipitation events, which lead to the deluges like we had in Toronto in the summer, which cost the insurance companies $800 million. The society costs are way beyond that.
We have the same type of changes happening over the last few decades that we had happening about 100 years ago in the high Arctic. One of the important ecosystem realities of this warming in places like Hudson's Bay is that there have been some fisheries, so a lot of native people use these fisheries, and over years these fish have been dying in summer. They're too hot. These fish are adapted to cold water habitats, and the lakes are changing their temperature properties, and so the fish are dying. So here's a direct, economic, if you like, or nutrition problem.
Singaporeans often curse at the sweltering heat and sudden heavy downpours, but now there comes a new reason to be concerned. A new study published in renowned science journal Nature said Singapore's climate will change irreversibly in as little as 15 years. Though other countries are predicted to experience a similar fate, Singapore will be one of the first to feel the heat.
As the climate is changing and we're changing those conditions in the atmosphere, it's just making everything more dynamic. More dynamic means it's going to be more variable. So we're going to have periods in a particular location that might have more storms, more intense storms. We really need to wrap our heads around the natural climate cycle. So a lot of these colder than normal periods that we experience now are because of things like La Nina and these sort of natural climate oscillations that are happening anyway. So how are they going to change? Those types of fluctuations are going to become more prominent with climate change. It's not just everything's going to heat up and melt. things are going to get really variable too.
The city of Manila has, they say officially 10 million people, but in fact they figure that probably there's 15 million there. And those people, those other 5 million, are coming and going. And most of them have no property. They're desperate for a job. They come to the city along the river basin. And those rivers are now flooding. The country of Philippines had 33, by UN official numbers, 33 disasters last year. Most of them flooding due to tropical cyclones, heavy rain events, flooding these rivers, and these poor people who have nowhere to go. They're desperately, their families, little kids, are living in this environment. And my God, the river comes along, they lose everything. And unfortunately, many of them lose their lives as well.
Professor Simonovich, what specific applications have you been involved with?
The studies that we have done are indicating that we may see the floods that may exceed the historical floods up to 20%. I mean, nowadays the most losses, economic losses experienced from natural disasters are coming from flooding. The major, obviously, risk is the risk to human life. The second important impact is on municipal infrastructure, including roads, bridges, and elements of infrastructure that support the regular functioning of individuals within these urban environments. Inundation of the road may prevent the traffic moving from one place to another place, or people being able to be evacuated. The third major source of damage is damage to the environment, and floods are obviously bringing considerable amount of water that may stay over the area for a period of time that can cause various potential impacts. If the land is being used for agriculture production, it may affect the agriculture production. If the land is used for different industrial activities, it may have some impacts on the kind of water quality that flooded water may carry with it to areas that may not be exposed to kind of these different chemicals. And the repetition of the events is sending a very clear message that a particular type of land use and rules and regulations will need to be changed in order to prevent or minimize the damage in the future.
We're going to have to think about issues of migration, and we've got all these borders, which were mostly put in for post-colonial reasons. If they made any sense before, they don't make any sense now in the climatic conditions. So you have migrations of people coming to a border, and the new guy says, no, you can't cross here because I got to protect my people on this side.
Our water resources have come to us over many, many years, and the climate that's been in this area at that time, and that climate's changing. So we don't know that our rainfall or our precipitation inputs are going to be the same. So all those bottles of water we're exporting out of here, we can't assume that equivalent amount of rainfall or precipitation is going to come back in to replenish that. So that's why you always try and keep the cycle in one place. Should we be exporting water from the Great Lakes to some of the drier states in the US, you're taking it out of that catchment that was constantly supplying and cycling water through itself. So I think the other thing we need to think about is let's start to adapt to what we're seeing now and what we think might happen.
We're already working towards the Millennium Development Goals with limited, in some cases, great success. And climate change is yet another challenge that's woven within poverty, within these systems. And we really look at adaptation in context of all these other stresses.
I really do think it's the major issue on the planet. We hear about terrorism and the economy. Well, let's not pretend that climate change is not going to affect the economy. It's going to be the biggest factor on the economy. Let's just make the list. It affects, agriculture. It affects forestry. It affects fisheries. It affects natural resources. It affects tourism. It affects health. The list goes on and on. It has very strong economic consequences, but those economic consequences has not been factored in yet. It's seen as some sort of cost to mitigate climate change. What's the cost of not mitigating climate change? That's what we should be asking the question. There is some denial that it's happening, but we have lots of time, and we have a much more important problem that we have to deal with, or the public doesn't see it as an imminent problem. Everyone has an excuse. Like, if we do it and the province next to us doesn't do it, then, well, we've given them an economic advantage, you know, and it all comes down to this. Well, at some point we have to start showing leadership, but people are very reluctant, it seems, to show leadership in this type of thing, and partly because they don't see immediate returns. You know, if you feel very justified in a war, you'll have some immediate returns if you win. If you feel very justified that something requires immediate economic action, they'll see relatively recent returns. What you're doing here, you're going to see your returns maybe in decades, centuries, or maybe even, you know, a long period of time. And we have a real problem doing a lot of action if we're not going to get credit for it.
Unfortunately, in our history of dealing with environmental issues, we tend to look at them one at a time. And we do something to solve that problem, and by doing that, we've made something else worse. This project that Dr. Simonovich and several of my colleagues are part of is called Coastal Cities at Risk Due to Climate Change. And our cities are Vancouver, Manila, Bangkok, and Lagos. And saying, okay, what's going to happen in the next 30, 40, 50 years, 60 years, to those cities as the climate changes? We've got a top-flight medical doctor professor looking at the health aspects, top-flight economist professor, and teams of scientists working together to try and build a way of figuring out how to optimize, how do you make it so that the strategies you take actually have the best social benefits, the best health benefits, and you don't leave something out.
Our research is applied research. We are more on the side of developing different adaptation options and developing tools and helping those who are making decisions. And obviously now our results are being taken by the consultants to further develop the technical solutions, investigate various adaptation options, and use our methodology for the assessment of climate change impact risk to compare these different alternatives and possibly advise the city what will be the best way to deal with the potential risks from flooding. The second important aspect that I think every country should be thinking of is giving space to rivers. In Europe, this is one of the really main directions of thinking. The traditional way of, living very close to the river, building some structural protections or barriers between the river and the population will not be working in the future. If we are using land for living very close to river and this land is becoming flooded very often, obviously rebuilding at the same location or rebuilding with the same type of technology or rebuilding at the same elevation does not make much sense.
Now they're taking action in Bangladesh. They're taking action to warn the people. They're building when they build a school, they now build the bottom floor, doesn't have anything in it. So when the flood comes over water, all it does is wash it out.
I think we've made very good progress on the Millennium Development Goals that correspond to water, but there's still a lot of progress that needs to be made. We're not at all in a sustainable state. In the parts of the world that went through the Industrial Revolution in the late 1800s, early 1900s, we have very substantial amounts of industrial chemical pollution, carcinogenic, highly hazardous compounds, chemicals that have been released and are contaminating our groundwater and making them unfit for consumption. These chemicals can lead to cancer and leukemia and all sorts of neurological disorders. These factories would be located right on the rivers and lake edges that would be in the center of town, and these sites are largely abandoned. So we have a big opportunity to clean those up and contribute to urban sustainability. The more we put into landfills, particularly hazardous materials, they almost inevitably leak into groundwater. So for example, we're making a lot of new products out of nanoparticles, nanocarbon, and all sorts of nanofibers are being used in new products, and we're putting those into landfills every day. We don't know the potential harm that could lead to down the road. I would say in the countryside, where there's a lot of farming going on, we have very different problems. We have a lot of nutrients, pesticides and organics that are contaminating the lakes and rivers and groundwater. And so there's a lot of research going on here on how much of those pollutants are getting into the groundwater in lakes and rivers, and how we can possibly reduce algal blooms, fish kills, deoxygenated zones in the less developed regions of the world, where there's a lot of poor sanitation and hygiene practice, where they don't have the infrastructure that we do for sewage and wastewater treatment plants And so there we're doing research really trying to help reduce infant mortality by improving sanitation in the developing world. At most contaminated sites, for some of the most toxic pollutants, we really have no good solutions. So what ends up happening is they come along with a digger and they dig up the soil. And it really isn't treated. It doesn't really solve the problem, it just moves it somewhere else. And sometimes you might have to dig up, hundreds of thousands of cubic meters of soil, when in fact only a small fraction of that is actually contaminated. So we're really looking at developing some innovative solutions. We have new technologies that have the ability to use very little energy, that we can use the properties of the contaminants themselves to destroy themselves in the subsurface. We can take advantage of bacteria, stimulate the growth of those naturally occurring bacteria, and have them consume the contaminants. And we can also look at things like injecting steam into the ground and other fairly innocuous materials that can interact with contaminants and help degrade them, and therefore restoring the natural functioning of the subsurface environment. We know that for every dollar you spend on investment in remediation, you get a $4 return on your investment in terms of boost to the local economy through environmental benefit, social benefit, and economic benefit. So the pays to be green, really, when it comes to remediation. We have a lot of field trials where we do a lot of field practice. We have a lot of computer models where we can simulate these systems. And we have a lot of new technologies like nanoparticles, and using thermal techniques and using solar panels. And we can integrate all of these technologies together into really innovative and some high-tech and even some low-tech solutions that can really make a difference in people's lives and really contribute to environmental sustainability.
It's one thing to believe in something, but it's another thing to actually do something about it. So what do you think makes people want to actually go through with the change and actually make an impact, as opposed to just knowing about it and learning about it?
One of the key issues that caused the problem in the first place is that we didn't think in systems. So the question is really, how do we work together, right? How do we create networks? How do we collaborate?
One of the things we have to consider at all times is just how interdisciplinary and at how many scales adaptation has to work. So the problems we're facing are bigger than any one person, any one discipline, but if we're going to have any chance of adapting to climate change, we need not just the full range of academic disciplines, but also the full range of stakeholders from civil society to governments on board.
To some, the problem appears overwhelming and the obstacles appear insurmountable. And I think that we as a human species, as a humankind, we need to be more hopeful and to trust our ability to deal with the problem.
As environmentalists, we tend to want to communicate the seriousness of the issue to the wider population, and that's important, but we also need to figure out a way to empower them so that they will be able to act on an individual level.
Right? Like how can we ensure that it leads to action rather than apathy?
And when we're looking at how we're framing the messages, we need to look at who our target audience is and what is going to motivate them into action. It might be financial motivation, and that's okay, or it might be more of an environmental motivation or motivation related to their family or health, and we need to figure out what that motivation is and reduce the barriers that would prevent them from being more environmentally responsible.
The Singapore Environmental Council has released a position paper to recommend a nationwide program to reduce plastic bag usage. Known as Bring Your Own Bag Every Day, the initiative includes a mandatory weekend charge of 10 cents per plastic bag in order to encourage customers to bring their own reusable bags.
What are the 3 key things that climate change activists can keep in mind when developing future campaigns?
So I think the first thing is know your audience. You really need to know who you're talking to, and more importantly, what motivates them and what their barriers are. Try to frame the message in a way that's going to empower the individual to take action. Don't just give people a problem to think about, you need to give them a solution. Something that's tangible, something that's measurable, that's something that they can tackle as an individual and feel like they are making a difference.
We need to adapt to climate change by taking actions to reduce the impacts, and where there are, gain the benefits.
If I'm in a boat that's sinking, I'm going to start bailing, even though not everyone is bailing out water. I'll start bailing, and I think we have to start doing that.